All right, welcome back. Next on stage is Dieter and Nikolai talking about vehicle-to-infrastructure Wardriving. I'm looking forward to it. Please give a warm round of applause, and the stage is yours.
Thank you. Hello, troopers. Thanks for having us. This is Nikolai, I'm Dieter. We both work at Fraunhofer Isaac as researchers, and we want to talk about V2X Wardriving, which we did the last couple months. So first, V2X, what is it? I'd like to have a show of hands of you. Who ever read V2N, V2G, V2I, V2X in some kind of way? Okay, I assumed that because you read it a lot. But now the question, who of you really did witness V2X personally? Less. Good. Because that's why we got to the topic. We always thought it was some buzzword flying around and no one is really using it, and we want to see whether it's really used. So, for the use cases, we asked the website of the German Autobahn what V2X is about, and it should increase road safety and traffic flow via hazard warnings, so if there are roadworks or if there's an accident. Alerts for emergency vehicles, so if you don't do your Rettungsgasse, so emergency vehicles can get to the place where they need to. And last of all, information exchange between vehicles and infrastructure. That's the V2I part. Like I said, I wasn't really aware that this is really in field at the moment. This is actually also from the, not from the Autobahn, from the ASFINAG, which is Autobahn in Austria. And they show some nice images how messages in the dashboards for the driver look like. So you have different things like there's, for example, there's a traffic jam, or also there's icing. So all kind of different things, persons on the road, and they should warn the driver. So how does that look like in the vision or in the current reality? Maybe. So you have the lights on because you're a stationary vehicle. Then the emergency vehicle wants to get there, activates a beacon. All vehicles notice the beacon. And then you can react to it because you know there's an emergency vehicle approaching from behind, which you couldn't see in the rearview mirror before. And so this go all smoothly and well, hopefully. The whole thing, maybe it's an automotive kind of thing because they like acronyms. It's a nice bowl of acronyms for you. Which I also often confuse, so keep that in mind and bear with me. So we stir that up and give you first a short introduction. Like I said, V2X basically is the cover for all kind of V2s, vehicle to grid. It's for charging, especially if you charge your vehicle at home. You want your vehicle to interact with the infrastructure and communicate with it. And then V2N or V2 the cloud, that's used for over-the-air updates or maybe how the current navigation and traffic jam situation is handled. Also telematics for the OEMs. Then there's vehicle to infrastructure. Infrastructure is everything on the road, like road signs, lights. And there's also vehicle to pedestrian, so for vulnerable road users like bikes or pedestrians, they could also carry around beacons that warn vehicles when vision is bad or something like that, or way ahead of them approaching. And vehicle to vehicle, so the vision is that all vehicles also can communicate with each other and exchange information. For this talk, however, we only focus on vehicle to infrastructure and vehicle to vehicle, because that's what we witnessed when we were sniffing. And we start with how is that done? So what's the technology behind it? And first of all, there's CITS. It stands for Cooperative Intelligent Transport Systems. That's the system that's used primarily in the EU and US. And it's based on Wi-Fi that you know. Because you can see there's the IEEE 802.11, which you know from Wi-Fi, or the different kind of Wi-Fis there are, but this is P. And to abbreviate it and confuse you more, it's G5 because it's in the 5 gigahertz band. This is decentralized and peer-to-peer, so really local communication. And because it's local and peer-to-peer and no intermediate, it has a low latency of less than 1 second for the messages. Then there's C, V2X, which also looks similar to CITS again. But this is cellular, and it's based on 5G, and not G5, but 5G. And it uses the usual 5G cellular network to exchange messages. But since there's also the base station involved and everything, it's centralized, network dependent, and has a higher latency. The latency values were from a survey that the ADAC did some time ago. I think it was 2003. The ADAC is the automotive club in Germany, and they did a survey, and I think it might be lower, but that's what they claimed. And this is also the approach that China takes, and most vehicles there are using. Today, because we're in Germany and we only received CITS traffic, and that's what our hardware was built for, we focus on CITS. So what are the players? Also from a survey from 2024 from the ADAC, CITS is mostly used by VW and the daughter brands, and by the Autobahn GmbH, which operates all the infrastructure in Germany, at least on the motorways. And other brands are focusing on V2X. This could be because they started with V2X in China as a market and started with it. I guess there are also solutions and stacks which can use both at the same time, however, which one is available. So what are the roles? The roles for the infrastructure are the roadside units, or RSUs. You see them in trailers that warn you for roadworks. You have them in traffic lights, or just along the road as a standalone unit. And then there are onboard units, which are the units that are built into the cars, or short OBU. Let's talk about the stack next. So we already mentioned it's 5 gigahertz band, but what's actually used? Here we can see the stack. The PHY layer is 108.11p, like I mentioned. It's 5.9 gigahertz. You have 10 megahertz channels. And currently, the one that's used for ITS is the one exactly at 5.9 gigahertz, which is also the control channel. Then above that, you have a GeoNet and BDPB. Bear with me, I'm Franconian. Those are hard letters for me. So those, you can imagine, those are the IP-TCP pair. So GeoNet is basically the IP layer. You don't have IP addresses, but direct peer-to-peer communication. So the messages are routed hop by hop by hop. And there's topologically broadcasted messages, which means you have a hop count, time to live. And then there are geographically routed messages. So you can say, I want to address all cars or all road units in one geographical area, and the stack tries to route them to there and send them only to the vehicles or RSU which help getting there. The BDP is for establishing and managing connections, or also designating which payload follows next. And the next payload is, in this example, I mentioned CAM and denim. There are many more. There are different message types. Most of them are ASN1 encoded and binary encoding. So UPER stands for Unaligned Packet Encoding Rules. ASN1 has different packet encoding rules. So if you're not familiar with it, it also had a lot of security problems in the past, at least the parsers for it. And there are many rules how values can be encoded with it, and different methods. And the interesting thing in the V2X stack or in the CITS stack is they are mixed. So some messages are encoded one way, some others the other way. I mentioned CAM. CAM is cooperative awareness messages. You can imagine that, like, maybe many of you know ADSB from flights, where you can track flights in your browser. They're similar to those beacons, what the aircraft sends. So it's basically position and general status information. Then there is warning messages, decentralized environmental notification messages, denim. Traffic lights use map extended messages and signal phase and timing messages. The map messages show the infrastructure of the intersection. And the signal phase and timing extended message says, yeah, basically what's the current state of the lights. And also prediction how they might change. So if you're approaching, they tell your car to maybe accelerate or decelerate to get the green light. There are many more. The only one that we witnessed is the in-vehicle information message, but that was not in Germany. So coming to CAM. Like I said, it contains basic information and information that needs to be transferred cyclic and often with low latency. So you have values that always have to be sent, which is the PDU header with meta information, how to parse it. A basic container. Station type is, for example, is it a car? Is it a truck? Is it an emergency vehicle? Reference position of the car, or whatever sends the CAM message, altitude sometimes. And then the high frequency container, which is called that way because it's sent with every CAM message in a high frequency. This shows heading of the vehicle, the speed, vehicle dimensions, and infos like that. And then you have optional containers which are not timely relevant, so you can send them at your leisure. The low frequency container has information about the lights, so whether the car is having the lights on or not, or fog light. And also path history, so from the reference position, delta values where the car previously was, because that's necessary. You want to get a picture of everything happening around you. And this is used so other vehicles know where the vehicle was and now isn't anymore. Special vehicle container, that's for the emergency vehicles or police or something like that. It's highly use case specific, so it's pretty open what can be in there. Then denim, those are event-based, so when there's traffic or something like that. Accident roadworks. The triggering conditions are specific also sometimes to the vendor. You have the meta information as well. You have when was the event detected and the event position. And optionally, you have the event type. Is it a traffic jam? Is it an icy road? A linked cause, which is a separate message. And then a location container, which is optional, also with the event speed. So if that changes, for example, roadworks that travel slowly or something like that. And then an a la carte container, which is similar to the special container earlier, where you could put all kind of things in there.
Okay, so then thanks for the introduction how CITS technically works, but we are a security institute, so obviously we are interested in the security of CITS. And a good message here is they thought about security, and there is in fact security inside CITS. It's built upon IEEE 1609.2, and it basically is located into the geo network layer, and it wraps the upper layers. And there you have then some options. You can either send it unsecured, which we obviously don't want. You can sign your PDU, or you can encrypt your PDU. However, so far we have seen no encrypted PDUs. However, most are signed. And again, the whole blob is then ASN1 OEAR encoded because they tend to like different encodings for different stuff. However, this is also a little bit of a privacy issue, so there are also some recommendations and considerations for privacy as well. And these standards recommend some privacy enhancing measures, but they don't specify what the vendor has to do specifically. So that's our understanding so far. Most vendors rotate their certificates used for this security layer it's valid for 7 days, and they're typically rotated more often, either on a time frame or when your vehicle enters into a sleep state, it rotates its MAC addresses, its station ID number, and again, the certificate. And the final and obvious solution from a privacy perspective is that it's an opt-in feature where you can just disable it inside of your car. So if you're worried that somebody might be able to track you using your CAM messages, then you can disable it in your infotainment system. So I think every security solution like this needs an PKI. So here's the obvious and obligatory PKI solution for that. We have our root CAs, and below these two different entities, one is our enrollment authority, which is responsible for enrolling your roadside unit or onboard unit and bootstrapping it with its initial key material. And you have your authorization authority, which are responsible for handling the short-lived authorization tickets, which are then used to sign the actual messages. And at least for Europe, this architecture is handled by the European Commission, which manages the trust list. And there is a CITS point of contact, which then contains the European Certificate Trust List. And inside of this list, you have all your different root CAs. And each of these CAs then can have one or more of an enrollment authority or an authorization authority. However, they are not directly linked, so you have to then first go from your root CA to their website or service they provide, and then get your information about the other sub-CAs from the root CA. And the European list does not contain all the information. And because this setup is still kind of easy, we add, or the CITS standards adds different layers. So you have your basic production level CAs, your test operation and rollout, that would be L1, and your L0, which are for pilot projects on a small scale. And we only got quite recently some L2 PKIs. So this is relatively new, which meant that Volkswagen decided we do our own thing, because L2 PKIs were not ready when they started rolling out CITS. So with this information, we can start and look at CITS actually. And how did we start? If we want to look into a new protocol, our approach is we go with what we have in our lab. So we have some SDRs, so that was our first step, tune them to 5.9 gigahertz. And luckily, there is a GNU radio implementation for the Wi-Fi standard, the 11P. So that already works for getting some insights into the CAM messages and inspecting what is being sent. However, that's setup-wise a bit cumbersome, so our second step was then to use Wi-Fi cards. There are some specific Wi-Fi cards, and the Partner Institute already did some heavy lifting there in providing some patches to allow for the 11P implementation there, which was still a little bit cumbersome. If you work outside, you want to go Wardriving, that's still a little bit of a cumbersome package with our mini router we used for that. So we packed it all into a nice Raspberry Pi platform we built. I mean, it's basically this thing, and now that's something you can carry easily. It provides us some RTC features, so we can track our different PCAPs, and we basically have a standalone setup with this, which bootstraps itself, and we can just take it wherever we want it. I already touched upon the Wi-Fi card, so basically it's multiple cards by Atheros, and the patch in a shorthand adds the channels to the driver, patches the wireless RecDB, and then puts the interface into OCB mode to act as the intermediary here. And so far, for this specific vendor, we found quite many Wi-Fi cards which work. So, I mean, there are at least, I think, 6 ones of which we know that you can just order and use them. So I think everybody of you should be able to get your hands on one of those Wi-Fi cards. So with that, we had our setup for capturing these messages. However, we wanted to have some more opportunities to get some messages. And luckily, we have our own vehicle at our institute, which we could use for testing and debugging our setup. And we started again in our lab. That immediately resulted in nothing, because without a valid GPS fix, your vehicle won't send any CITS messages, so you have to provide some GPS information for it to work. However, then you can trigger some CAM messages and also some denims. However, for those, you need the specific conditions, which are vaguely described in the standards, basically. So we found out for the stationary vehicle warning message, you have to have your warning lights on and to open the driver door as well. And then you get into the problem of displaying these messages, which is even more difficult because the decision logic of when to display them is vendor specific. And most of the time, they consider things like, is this on the same lane and even relevant for our driver? OK, so how does this look then in practice? If we look at such a message, that's a CAM message. You can just open it up in Wireshark, and you see our secure packet and our CAM parameters, basically, and the different containers Dieter already talked about. If we dig a little bit deeper, we go into our secured packets. Those are the highlighted parts, are the interested parts for us. So this signer digest tells us that's a Volkswagen vehicle. The validity period obviously tells us how long our certificate is valid. And the app permissions tells us what functions this certificate can sign. So the first one tells us CAM, and the second is a bit bit mask for all the different denims and types of denim this vehicle would be allowed to send. And the other side would be our payload, actually, our CAM message. And there you get your reference position, your speeds, all this information. However, that's kind of difficult to digest. I mean, it's the car is sending out a CAM message every second around, and then you go through Wireshark and you're trying to see what's changed. And the obvious solution for that is to build a map. So,
black that out.
Yes, thanks. So we built a map for that, and it allows us to easily digest the CAM messages. So, for example, that would have been a drive through Munich and all the different messages we've seen on our way. Or then more closely, if we go to our institute, you could look at them more precisely and also display some meta information like which type of vehicle was it, what was the station ID, what's its MAC address, how fast was it driving.
Thank you. So when we first were driving, first waiting for CAM messages around our institutes and later driving around to get more, we only noticed CAM and denim, which are the most popular, I guess. And then suddenly there were also new messages, and we found some traffic lights that also were CITS enabled and sent MAPM messages. So how does a MAPM message look like? It's a lot of lists of lists of lists. Maybe that's why they chose ASN1, because it was easier for them then. So you have a list of intersections, which is usually only one item, because one RSU only is responsible for one intersection. Then you have each intersection has a name, an ID, also reference points and coordinates, and a set of lanes, so 21 lanes in this case. And how do the lanes look like? There are also lists of lists of lists. They have lane attribute as a bit mask. For example, is it for a vehicle? Is it for pedestrians? And so on. The directional use, so is it a one-way or how can you drive on it? And then there's a node list given here, which is basically just around the reference point, a set of delta points where when you connect the dots, you have, can draw the lanes. So back to our map, we connected the dots and drew the lanes. And then we can see how that looks like more human-friendly. Here you can see an intersection with a highlighted red one. That's a lane for vehicles. It's for motorized vehicles. It has the signals assigned, which we come to just in a few seconds. And it connects to other lanes, and those are in green. So it also tells the vehicles how they can drive and which maneuvers they can do. Can they do a left turn? Which lane are they ending up? So that's therefore, if you want to have the predictive green light function, then it's important that the vehicle knows which light is relevant to it, and then it can compare it with the navigation data where it wants to go, and choose the lanes that are relevant. Yeah, that's just another example. You have, for example, also one lane that splits in 3. And yeah, basically it's only the, how is the intersection built. Then the next message is the spatum, which tells what are the signals for those lanes. So we earlier saw that a lane has assigned signal group, and here are the intersection states with signal groups. It has 12 states and different movement states. And you see at one time it has separate states, even once there are predictive for the future. So it has a current state, for example, stop and remain, which is a red light. And then you have pre-movement, which is for German lights, it's the red and yellow combination, and the assumed time when this will happen. Also difficult, we tried also to plot this. That's getting very difficult very soon, because you really have to track the correct states and which is revoked and which is not. We just, to get an overview what's happening, we tracked all future states in the dotted form, and the current state or past states over here. All right, then I also mentioned we also got IVI messages, but not in Germany. I had to go on vacation to get those. So what we see is the Brenner Pass, which has a lot of those. I have to say, in Austria, there's much a wider deployment of V2X already, especially from the infrastructure side. So when you go on the motorway there, you receive the first messages, and they already tell you about like 100 kilometers later what's the situation there. Connecting the dots didn't work here. I assume they want to save some bandwidth and just do a shortcut here. So what the IVIM messages contain, they contain region of interest. So those are the different regions, and have a separate container which describes it, which we can see here. Here we can see GLC and GIV. GLC is the geographic location container, and the other one is the general IVI container. So here you can see 2 points, for example, the start point and the end point, with a heading. And for this part of the road, there's the regulatory message of 40 kilometers per hour restriction. There are many different more. For example, road configuration containers, which tell you which part of the roads are closed, or where you have diverged from your route. And also interesting, especially when you're looking at the PCAPs as a human, the text container, it's just plain text what the road signs, the interactive road signs tell you. So if there's no fuel at station XY, it's just the plain text in there. Right, then to our data set in general. So of all the PCAPs we sniffed, we tried to run some stats. According to the destination board of the BTPB, we have most of them are CAM messages, which is expected because every vehicle always sends the position and heading and everything else. There were around under 5% denim messages, so warning or event-related messages, and a rather high amount, because it was just 2 drives. It was one to the vacation location and the one back home. And there was, from packet-wise, already 7% IVI messages. So those roadside units are really busy. Coming to security, what did we observe there? We have the signer info and the signature type. Signer info is you can use also to save space. You don't always have to include your own certificate, but only a hash of it. So vehicles that already know your certificate can check this with a cached one. And vehicles that don't have it can request it in the next message. So most of them have the digest, which is blue, and some of them were sending the certificate. Signature type, there are two different ways of how to do the signature. The one is NIST P256, and the other one is Brainpool. So most of them are NIST. And what you notice, the 80%. So there are some messages missing which don't sign. So use totally unsecured packets. So why is this? Our assumption is that's still sandbox deployments or test deployments, because they were from some of the lights we received. And those traffic lights had weird names, which we assume are just for testing purposes. So they send out messages, so they can do measurements and interference checks, whether everything is all right. But the vehicles throw them away because they are not signed, hopefully. We didn't, with our vehicle, we checked, our vehicle wouldn't accept unsigned messages. Then to the station types. Most of the stations are passenger cars driving around. Then we had a single light truck, which is orange, which you can hardly see here. Some trailers, and the rest were roadside units, those sending the IVI messages or the traffic lights. Stats about the vehicles, because every vehicle sends its dimension. We plotted those. And additionally to that information, how long the vehicle also sends the information, whether it thinks it has a trailer and whether that measurement of the trailer is included in the length already or not. What we also found, I plotted only this region because there were two outliers. We also had that one light truck, which was 8 meters in length. And then we had trailers that said they don't know how big they are. Then to the message I told you about the trailer presence. Most of them don't know whether they have a trailer. There are two different kinds, how they can say it. The one is unavailable, which means I have no idea whether I'm able to pull a trailer, nor do I know if I have one. The other one is trailer present is unknown. That's the vehicles that think they could pull a trailer, but currently don't know whether they do. And then there's 0.1% of messages that were sure there was no trailer present. So it was interesting to look that back up what kind of station that was, and those were trailers themselves. But they were sure about it. Okay, then Nico can continue.
Yeah, so with this data, we were then able to do some correlation and enhance our map and our analysis further. And the first thing is that a car does not really say what type of car it is, but you already saw that the length and the type of the vehicle is relatively distinct. So we can use this information to look at the signer and say, okay, it's a Volkswagen and it has a length of X and a width of Y. So most likely it's an ID4 and it's a passenger car, so that seems to fit. So we use this to enhance our analysis and say, okay, that's most likely an ID4 car. Which is information would be interesting if any of you has a car and has the opportunity to get some chems or get us interacting with this car. We'd be really interested in some confirmed values and maybe look at some different types where we could enhance these analysis. The second thing we've done is the question we get all the time when we talk about this topic. Wait, my car is sending out its speeds. Can the police use this to track me? And as far as we know, no. I mean, that's not really an efficient way for them to do this because they have to be present at this position, and for that they can also just use the radar gun there. But, I mean, we could. So we built a small tool which takes the information from the cam, the position, the heading, the speed. We go with the position and the heading to OpenStreetMap, look up, okay, what would be the max speed for this way, and use it then to populate all this information and also add it to our map. That led us to some interesting findings. So we are here in the region of Munich again, and we look at the A99, and we have a vehicle there. It's an ID4 most likely, and we look at it in more detail, and it's driving over 580 kilometers per hour against the flow of traffic here in the between the lanes. And if you look at its orientation, it's also drifting while it's doing. So obviously, it's been an Italian plumber who was driving there. So that's the only option for that one, I'd guess. And also, we used our tooling and our setup to utilize it here in Heidelberg, and we used every opportunity we got to capture some cams here. And if I say every, I mean every opportunity, so we even used the 10K to get some additional information here. And I'd like to show you this. So we've prepared a small demo. So let's see. Grab this quickly. And that's basically our map. I've already uploaded all our PCAPs. It's automatically processed. I disabled our speed check just that I don't query OpenStreetMap so often. And we can then use it and investigate a little bit of Heidelberg. You can already see where is Troopers located, where did we do our 10K, and get some additional information. For example, I think in Barnstadt, we see a vehicle right here. It's one of those which I think was parking there at one evening, and it enabled its warning lights and triggered then the denims in orange, which tells the corresponding vehicles around this area that there is a stationary warning, there's a stationary vehicle which is parked basically next to the subway, where they maybe quickly got out and got a subway. And I think I already handed over back to you, and you talk a little bit more about the security.
Yep. One thing was, well, interesting for me, because I was always interested in the infrastructure side of it. We didn't find any road units in Heidelberg operating. So maybe next Troopers. So what's next? We do security research. What's it like to test the security of CITS? So up until now, we only received the packets and analyzed them. When we want to test, we also need to send them and however we want. So we used Skeppy for that. Built our layers on Skeppy. Some are very easy, and I'd say Skeppy compatible, like at the BDP, because they are just simple fields, like a TCP/IP packet. You can model them quite easily. We built custom layers, at least for CAM and Denim. I think a few others we tried as well, but those were the ones we definitely have. It was a bit complicated because of the ASN1 troubles. Skeppy only supports BER and DER encoding, which is used for all kinds of certificate stuff, which Skeppy supports. But CITS also uses the other encodings. So it was a choice of implementing ASN1, the other ASN1 encodings from scratch for Skeppy, which was too much effort for that what we wanted to do, because we didn't want to go that rabbit hole and wanted results and really tests. So we tried to find shortcuts. So the current solution is using ASN tools, Python library for ASN1. We adapted the official ASN1 definition, which you can get from the Etsy. So we can use ASN tools to import them into Python. And then we botched a bit around with Skeppy. So we have hooks that handles the ASN1 fields and creates dicts of it. So it's everything that's one AS1 blob into a packet, you have one SCAPI field which contains a dict. And that was good enough for us for the start to start testing. So it's not desirable, but works for us. We wanted to test whether unsigned messages are received by cars. So we wanted to do emergency vehicle spoofing. And like discussed earlier, it's necessary that the trace makes sense and it aligns with the car. So you really have to build a line of dots where the emergency vehicle should drive. It was too complicated to do by hand. So we built a tool which you can give GeoJSON. It extracts position, speed, and heading, and creates the different color is CAN and denim messages, and you can route the emergency vehicle where you want and check whether the vehicle displays something. Unsigned messages were not displayed at all. We also had a valid certificate for the sandbox environment, I guess. Yeah. So we assume maybe when we use the sandbox that the car is backward compatible and would allow it, but we couldn't trigger it as well. Maybe there were some other missing conditions, so if any one of you has further information, what are additional conditions, what the car needs to display those messages, we would be happy to get them. Then we come to fuzzing. We also wanted to fuzz the stack because it's AS1. You can start with native fuzzing. You just throw Radamza at a CAM packet in SCAPI and see what happens. You can be smarter and directly target AS1 because the thing is, like Nico said, all the security, all the signing is happening, and then that's still encoded in an AS1 blob. So at least one AS1 parser needs to be active before the security checks can even happen. So we messed around with the type length value fields. And after that, you can do also payload fuzzing. But like I said, most serious vehicle throw the unsigned messages away, or when you don't have a trusted certificate, which is quite hard to get. So payload fuzzing is currently a bit out of scope. Also, when you do fuzzing, you need a back channel because we are doing black box fuzzing. We have the car there. We don't have any debug interfaces. So how do we solve this? We get the car to send CAM messages periodically. Then we define a bounding box where we assume that our car is. So when they are, for example, at the road driving by other cars, that you don't detect those as your heartbeat. And then when you have the station ID of your car, you can track the cyclic cams, whether they're still appearing. And if a cam is missing, then you can raise the flag, log it with the payload you just send it. Else you go back to the bounding box, because when you crash onboard unit, it might be that it gets a new, because of all privacy features, it gets new certificate, station ID, and so on. So to track it again, you have to start with the bounding box again. So what are limitations to that approach? I mentioned that it's the fuzzing depth. You have multiple stacked parsers which might be vulnerable and unstable, but you only hit the first layer usually, except you can go deeper with valid certificates or trick the car into accepting a certain certificate. So targeting deeper layers is not trivial. For the end, I think time is okay. For the end, a disclaimer about the radio emissions. When you do fuzzing, of course, we were aware that we don't fuzz every vehicle in the vicinity of our institute. So mind your local regulation, which might be different for you. For Germany, we have the Allgemeinzuteilung. So we acted upon this as good as possible. And we limited our transmit power on the interface. And the tests that were able to run indoors, we used indoors. So to come to our conclusion of the talk, and what would we release with it? We used a lot of software that helped us a lot to get to this point. So the first one is from the HPI Potsdam, which we already mentioned, which is basically the whole patching of the Wi-Fi drivers to go to 5.9 gigahertz and use the correct channel without a base station. The one below is the repository for the SDR, and of course Skeppy. And instead of releasing our own kind of thing, we thought we contribute back to those projects. So we did a minor patch to the 800.2.11p repo, so that patching works straightforward with the Raspberry Pis we were using, and which also you might be using. And we still try to get our layers into Skeppy. Like I said, currently it works for us. It wouldn't make sense to push it into Skeppy as it is, but I also talked to one of the maintainers of Skeppy, and yeah, we try to find an elegant solution for this. And recently, before our talk, we stumbled upon the project Open Traffic Map. It's from some researchers in Graz. And you can see that's a small movie from their interface. It's really like a flight tracker. In Graz, there is a lot more of CITS deployed. So also public transport uses it. Lots of infrastructure use it. Also some bikes are driving around. But I think that's from the maintainers of the project. So all map-related stuff, we try to contribute to them, because that's a really nice-looking project. And they also do it in real time, which is nice. If it's not possible to get a standalone map within the scope of the project, we plan to release our proof of concept on our GitHub sometime, but that's not the goal right now. We'd rather contribute to those guys. So to wrap it up, this should be a small introduction to get you interested, to also start sniffing CITS traffic, maybe fuzzing CITS traffic, maybe collaborate with us. There's a lot more to explore. Hopefully you're interested. If you are, talk to us. Those are our contacts. And if there might be the POC of the map available, you'll find it at our GitHub. So thanks for your attention, and we're happy to answer questions.
All right, already got the first questions.
Hi, I don't know if you saw it, but a few weeks ago the guys of OpenStreetMap released a firmware which can send ICTS traffic, and I don't know if it's practical for your use case.
Maybe you mean those guys? Yeah, because what we saw also on their wiki, they are not only using, or they're primarily using ESP controllers. So maybe if the Troopers badge supports 5G sometimes, maybe we can include it there with their repo. We didn't have a look at it, what you can do with their stack, but if you say you can also send messages, we have a look at that, how they do it. Thanks.
Thank you for the good talk. I wanted to ask about reading out the certificates from the car. You said it's pretty hard, and I mean it's good to know that unsigned messages are not like trusted, at least for the car you tested. So it would be interesting, like especially if the certificate is updated often, if there's a way to extract it, have you tried it? Yeah.
We did not try it yet. That's on our to-do list, because we also had a look what happens inside the car with the different ECUs that are involved with it. We saw, for example, it was not only the GPS location that was missing when we tried it indoors in our garage. It was also because of the missing GPS location and time, it didn't have access to the backend servers to get new certificates. So we might look there deeper.
Okay.
And maybe a small extension on that. We've assumed that certificate storage is quite hard to get because they will store it most likely securely, but I haven't done EMCC on my workbench, which I'd like to work a little bit more on, because I think that might give us some additional insights of how the car actually handles its updates and its mechanisms.
Thank you for your talk. This looks like a potential privacy issue. You demonstrated fingerprinting based on applicative layer messages. Is the .11p layer using physical identifiers like MAC addresses or something like that could be tracked?
So they're rotating the MAC addresses regularly, and about everything which would help you in identifying a car is regularly rotated. So you would have to be present and track the vehicle at its location as well, so that you're able to link that the vehicle that left or arrived at this point and left later is still the same vehicle, basically.
Yeah. So the thing, we got this question a lot also before, how the tracking works, and it boils down to really track a vehicle for sure. You have to follow the vehicle, and then you're tracking it anyway. So